And Nick, let me start share screen in the usual evening procedure here. So let's get this share here. All right. Let me magnify a little bit. Let me put it in focus if I can. Does that focus it? I guess it did. All right. Let me get the right pen. Okay, so this page has some summary of where we were. We ended in the midst of a lengthy calculation. We're studying the scattering of photons from an atom. An atom is in state A. A photon strikes it. The photon scatters into a new mode, photon gamma prime, and possibly changes the state of the atom to a new state B, which could either be higher or lower in energy, depending on what A is. If A were the ground state, then B would have to be an excited state if it were different. Anyway, we call the mode of the incident photon lambda, which is otherwise K mu, and the mode of the scattered photon, we call it lambda prime, is K prime mu prime. So the primed and unprimed modes refer to the incident and scattered photons. And here's a geometrical picture. What it looks like in real space is the incident photon comes in, strikes the atom, goes off, scatters at an angle, gives a wave vector K prime and angle theta. If the scattering may be inelastic, if B is not equal to A, then there's some energy that's involved in making the transition of the atomic state. And if that's the case, then the outgoing photon will have a different energy, and therefore the magnitude of K prime than the initial photon. And therefore the magnitude of K prime would be different than the initial one, or the frequencies, if you like, omega prime would not be equal to omega. Anyway, this is kind of the basic setup then. So we're analyzing this using time-dependent perturbation theory and switching back and forth between the general notation that we used in developing the theory, time-dependent perturbation theory, and the specific notation for this problem. So in the general notation, I is the initial state. For this problem, it's one where the atom is in state A, and there's one photon in the field in mode lambda, which we can write in various ways as A times lambda, or just simply A lambda. I'm using here the convention of using capital letters for the atomic states A, B, and later on you'll see another one appearing too. But in any case, the photon states are given by applying creation operators to the vacuum. The final state, which in the general notation we called N because it's a variable final state, is one in which the atom's in state B and the field has one photon in mode lambda prime. Otherwise, we call this B lambda. The Einstein frequency connecting the initial and final states is just En minus Ei over H bar, and that's the omega plus omega Ba minus omega prime. If the scattering is elastic, then B equals A and omega Ba is 0, and then it's just omega minus omega prime. In any case, setting omega Ni equals to 0 gives you as usual in this business, it gives you the conservation of energy condition. Then we did a fair amount of work in the last lecture on now using second order time-dependent perturbation theory to obtain an effective transition amplitude. This is otherwise an effective version of the matrix element of the time evolution operator and the interaction picture between the initial state I and the final state N, except it's effective, which means that we're omitting the terms that correspond to transients and keeping only the ones that will result in a transition rate. If we do that, then we get this characteristic, somewhat complicated looking, but characteristic time-dependent factor out front, which is the same thing that we had in first order time-dependent perturbation theory, multiplied by some matrix element stuff. And in the first term, what we have is the second order Hamiltonian K2 taken in first order perturbation theory. And then the next term, which is of the same order of magnitude, is the first order perturbing Hamiltonian K1 taken in second order perturbation theory. Here's the Hamiltonian broken up into the three terms K0, 1, and 2. And they're ordered basically by powers of the electromagnetic field. The vector potential and B are considered the same order here, and the A squared is a second order. This is the ordering that you use in the coupling with the electromagnetic field. And as it turns out, it gives rise to a power series expansion and powers of the fine structure constant. Is typically how it works out in typical quantum electrodynamics problems. All right. So the first matrix element to work out is the matrix element of K2 between initial and final states. That involves the square of the vector potential of the product of two Fourier series. And we worked that out last time, and it can be written out. This is the result. It's some factors that come from the perturbation here, you see right here. Prefactors on the Fourier series for the vector potential. Square root 1 over square roots of frequencies, which is contained inside the Fourier series for the vector potential, and then dot product of polarization vectors, and a Kronecker delta between the two atomic states. There's some comments I want to make about this result. One is that we've been deriving this result, we use the dipole approximation. The dipole approximation amounts to saying that Kr, or K dot R if you prefer, is much less than 1. And this is a condition that obviously depends on the value of K, which is related to the energy of the photon. Back when we were doing spontaneous emission of photons from an atom, the K was determined by the difference in energy between the atomic energy levels. And in that case, this condition is well met, easily met. In fact, K is nominally of order alpha, of order the fine structure constant, and problems like that. In this problem, however, there's an initial photon omega wherever it is up here in this mode lambda, initial photon frequency omega. Here it is, and this, of course, could be anything. It could be high or low. To be specific, let's suppose we're talking about optical photons, or no, not higher frequency than that. If we do so, then this condition, K dot R being much less than 1, is easily met, as it is also for photons of lower energy, for example, infrared. If you want to do infrared scattering, this works just as well. On the other hand, if you wanted to talk about X-rays, then this wouldn't be true anymore, and you wouldn't be able to make the dipole approximation. In any case, the dipole approximation means that all the factors of e to the IKR, or plus or minus IKR, for example, which occur in the vector potential, can just be replaced by 1. And it also means that the spin term, which is contained in K1, can be neglected because it's also of order of the wave vector K, if you'll recall what we did in the analysis of spontaneous emission. So we'll neglect the S dot B, and we'll set e to the IKR goes to 1, and this will be valid at optical and at lower frequencies. And having done that, then we get this expression for K2, and that was one of our main accomplishments in the last lecture. All right, now I'd like to begin tonight. So now what's left to do, you see, is to work up the sum, which is the second major term in the transition amplitude. It involves a pair of matrix elements here. We'll work on that in just a minute. But before I do that, I want to say some things about Feynman diagrams. So let me bring back some summarized sheets that I have here. Here is one. Let me get a clean piece of paper and to work on this. And what I've done here at the top of this page is just copy for you the formula for the Dyson series for the transition amplitude, to make a transition from initial state I to final state N. Excuse me, as a function of time, organized into orders of perturbation theory. Here's the 0th order term, the 1st order term, and the somewhat complicated looking 2nd order term. And there is an interpretation which is given to this. This is the Dyson series. There's an interpretation which is given to this. I'll remind you that these phase factors that occur here, for example, in the 2nd order term, they arose when we took matrix elements of the Hamiltonian, the perturbing Hamiltonian, in the interaction picture and converted it into the Schrodinger picture. That's where these phase factors came from. And then we did the time integrals, which I worked on in the last lecture in some detail. This is the general structure. in examining these formulas, there's a point of view in looking at them. Let me point out a couple of things. First of all, in the first order term, which is up here, there's three times that are under consideration. There's the initial time 0 and the final time t, but there's a variable time t prime, which is a variable integration that runs between them. So the times are ordered by the fact that, let me do it right. The times are ordered by the fact that the t, the final time, is greater than or equal to the intermediate time t prime, which is greater than or equal to 0. There's an ordering of times like that in the first order term. In the second order term, there are two intermediate times, and they're ordered like this. The final time, do it again, do it right. The final time t is greater than or equal to the first intermediate time t prime, which is greater than or equal to the second one, which is greater than or equal to 0. There's a sequence of times like that. You can see that t double prime has an upper limit of t prime, and t prime has an upper limit of t because of the ranges on the integrations. So if you want to go from the initial time to the final time, people read these matrix elements backwards. And here's an interpretation that's given to this. Is we say that at the initial, at I here is the state of the system at the initial time 0. We say that the system stays in that state up until time t double prime, which is a variable of integration, up until t double prime, whereupon it interacts with h1. And that converts the state into an intermediate state k. And then it stays in intermediate state k up until time t prime. T double prime was the first change, up until time t prime, which is a variable of the second integration, whereupon it interacts with h1 again, which converts it into the state n, and then it stays in state n up until the final time t. It's simpler for first order because you just go from the initial state I at time 0, interacting at time t prime with the inner perturbation once and converting into the final state, which then stays in until the final time. And so these interactions occur at different times, but the integrals mean you sum over all possible times at which those interactions can occur to give you the contribution to the transition amplitude. Now this leads to the concept of Feynman diagrams. The Feynman diagram is basically a space-time diagram. And I'm going to illustrate it by with the n k2I. That's this first term here, which we worked out and got this explicit answer down here below. We worked it out in the last lecture. I'm going to present you the Feynman diagram for that. This is the second order Hamiltonian taken in first order perturbation theory. So we'll make time run vertically like this. I'll have the 0 time here. There's an intermediate time t prime here, and a final time t here, which is the last time. Now at times you can think of this as being the time direction and this being a spatial direction if you want, as if it was a space-time diagram like in relativity theory. Now at the initial time we have the atom is in state A, and the photon field has one photon with mode lambda in it like this. And I'll just put dots there to represent that. The idea is that the photon interacts with the atomic state at time t prime. We'll show this interaction as if the whirl lines of the photon will indicate the photon whirl line is a wavy line and the matter whirl line is a solid line that come together and give us an interaction at an event that takes place at time t prime. And at that event, what happens is that the initial state is converted into the final state. Well, the final state has the atom in state B, and a new photon in a different mode, lambda prime, has appeared. And so we get a conversion like this that takes place at this intermediate time. And this gives us the Feynman diagram corresponding to this term of the perturbation expansion. This diagram is called the seagull diagram because it looks like a bird with wings is the idea, and feet, sort of roughly anyway. It's called a seagull diagram. And you can see it has a 4-point vertex. At this vertex, there was an annihilation of one photon and the creation of another one. That came because the K2 has an A squared in it, vector potential squared. And when you square them, you get all combinations of pairs of A's and A daggers, and it includes an AA dagger and an A dagger A. There were two terms. I'll remind you, they gave us contributions that were equal to one another. And the A is going to destroy the incident photon, and the A dagger is going to create the outgoing photon. That's what happened right there. All right, so this is the Feynman diagram for the term that we worked out in last lecture. Now, let's turn our attention to the, let me put this away for now.
Wait, I have a quick question.
Yes.
So in quantum electrodynamics, you only get a 3-point vertex. How come over here we're getting 4 points?
I'm sorry, what?
How do you coincide the fact that in quantum electrodynamics you get a 3-point vertex, and over here in the seagull
Well, in
you have,
quantum electrodynamics, you don't have a squared terms. You just have a terms.
so is this
If you hang on, I'll say something about that at some point in the next several lectures. I'll be telling you about that.
okay? Sounds good.
Yeah, it's actually quite interesting. This is non-relativistic QED, and there you get the a squared terms because the kinetic energy is p minus a squared, and the a squared term has two products of vector potentials, and that creates or destroys two photons, either one or the other. It handles two photons. That's why you get a four-point vertex. It could either create two photons, destroy two photons, or destroy one and create one. In this application, it's the latter possibility that is realized, and this is what you get. You could also have it destroying two photons. You could get diagrams that look like this, or even like this. You see, from the a squared term, you can get that 4-point vertices look like that. All right. All right. Now let's see. Yeah. So the next goal then is to analyze the remaining terms of this results from time-dependent perturbation theory. The other amplitude contributions to the amplitude that occur at the same order. This is, as I said, was K1 taken in second-order perturbation theory. Now I explained part of this last time at the end of the hour, but I'll go over it again as briefly as possible. We've got a product of matrix elements. Here's the initial state if we start from the lowest time. And then there's K1, and then there's a sum over intermediate states. The sum over intermediate states came from a resolution of the identity. So it technically, or in principle, this involves a sum over all the states of both the matter and the electromagnetic field, including all possible states of all numbers of photons going from 0 out to infinity. However, most of those don't contribute. And the reason is that our particular initial state only has one photon in it. And the operator K1 is a linear combination of an A and an A dagger, because it's basically K1 here is equal to E over MC times P dot A. And the vector potential has the linear combination of a creation and annihilation operator. So K1 can only create one photon or destroy one photon. Now, it can't destroy a photon unless it destroys the photon that's already in there. It's got to be the incident photon because there's no other photon to destroy. So if K1 destroys a photon, then the intermediate state K, lowercase k, can only contain no photons. It has no photons at all. On the other hand, if K1 creates a photon, then it creates a second photon in addition to the initial one. And so then the intermediate state K has two photons in it. And thus we end up with two cases. Let's call it case one, in which the intermediate state K is equal to an intermediate atomic state in which there's no restrictions on what that can be. Let me just call it capital I, again, using capital letters for atomic states, multiplied times the vacuum. No photons in the intermediate state. Case two, however, is one where the intermediate state K is equal to an arbitrary intermediate atomic state, I'll call I, multiplied times a two photon state, of which one of the photons had to be the initial photon because the first K1 is only going to create a second photon. So there's a second photon in there. And it turns out that second photon must be in the mode of the final photon. It must be mode lambda prime. Why is that? Because when we come over to the second matrix element, if K has two photons in it, one of which is the initial photon, then this second factor of K1, it has to destroy the initial photon because the final state doesn't have the initial photon in it. It's got the final photon in it. And so the one that's not destroyed had to be the final photon. That's why this is a lambda prime here. That's what it has to be. All right, so this is case one and case two in the analysis of this matrix element. Now, given those facts, and if you can remember what this matrix element looks like, it's easy enough to write down what the Feynman diagrams are. Let's take the time going vertical here like this. let's have the time 0. We have two intermediate times now. We've got a t double prime is the first one. The second one is the t prime. And the final one is time t. And at the initial time, we've got the two states, A, or well, the atom is in state A and the photon is mode lambda. Now, what we decided is that at the initial intermediate time, at time t double prime, we had to destroy, in case 1, we have to destroy the initial photon. So we've got, they have to come together like this. Their whirl lines have to cross in order for this to happen. They come together and the initial photon is destroyed. And then what happens is that we make a transition to the intermediate state, which has an intermediate atomic state and no photons at all. So what we have then is it turns into something like this, where there's just an atomic state I. And then at the second time, second intermediate, later time, intermediate time t prime, we have to create, in order to get, when it comes to state n, in order to get the final photon, we've got to create the outgoing photon. So it has to look like this. Here's the atomic state B. Here's the lambda prime for the outgoing photon. That is created at the second vertex like this, and the atomic state B does this. So this is the case 1 Feynman diagram, like that. Now in case 2, where we have two photons in the intermediate state, the difference is we got A and lambda down here. The initial state is always the same, and so is the final state. We have a B and a lambda prime here. But what happens is at the first intermediate time, the A goes up here. Instead of destroying the initial photon, instead we create the final outgoing photon like that. And the atom turns into intermediate state I. Now, as I said, the second photon is the initial one. The initial photon gets destroyed at the second intermediate time, so you get this kind of a diagram here for that. And then the atomic state then converts into I, like so. So this is the Feynman diagram for case 2. And you can see the difference between these two diagrams is that it just has to do with the ordering in which the initial photon is destroyed and the outgoing photon is created. They just reversed one another in comparison between these two. All right, so those are the diagrams then. Now then, if you've got the diagrams, then it's fairly straightforward to work out in detail what the formulas are for the amplitudes. You need to remember a little bit. I haven't written it down. I've written it down so many times already. I haven't written down for you the Fourier series for the vector potential, wherever it is here, A of R. But hopefully you remember some of the details of that. And then the K1 has got this E over MC prefactor here, and there's prefactors in the Fourier series. But you can kind of work this out without too much trouble. Let's take the matrix element on the right first. So let's look at the K, lowercase k, K1I, like this. This is the same thing as intermediate state for the atom, empty field, like that. That's what that K is in case. I'm doing case 1 now, case 1. And then the K1 is E over MC times P dot A. And then the initial state is the atom is in state A, and we've got an A lambda dagger applied to the vacuum to give us one photon in mode lambda. So that's what this looks like. Now, by looking at the diagram, you see that at the first intermediate time, we're going to destroy the initial photon. So that means that inside this A, we need the annihilation operator to annihilate that photon in mode lambda. And if you recall, that's connected with a polarization vector, epsilon hat lambda, and a factor e to the I k dot r. K dot r is the position of the electron, but that's because the vector potential is evaluated there. Anyway, these are factors that occur there. So the momentum is going to get dotted into the polarization vector, and e to the I k r will get eliminated by the dipole approximation, just gets replaced by 1. And so if you remember those kinds of details, oh, and then by the way, if you look at the field part of the matrix element between the two vacuum states here, you have the vacuum expectation value of an A lambda from the vector potential, an A lambda dagger from the initial state, and a 0, and this is just equal to 1. So all that's left over then is an atomic matrix element, and it's going to look like this. I'll take the E over MC first, this factor. Then there's the square root that's in front of the Fourier series, 2 pi h bar c squared over volume V. there's 1 over the square root of frequency omega. This omega without a prime on it refers to the frequency of the incident photon, and that's because that's what goes along with this term of the Fourier series. Then we have atomic state I on one side. The matrix element is beginning now. We have the momentum P dotted into epsilon hat. I'll omit the lambda. Epsilon hat means epsilon hat lambda. And then we have atomic state A on the other side. So this is what we get for this first part. It's this first matrix element of the 2 that we need in this second order sum in case 1, like this. Okay. Now then, if you do the same thing for case 2, what you're going to get then for case 2 is in K1, K, like this, for case 2 is going to be equal to E over MC, square root of 2 pi h bar C squared, some of the same prefactors. We get 1 over the square root now of omega prime, because what K1, the second K1 does is it creates the outgoing photon. As you can see from the Feynman diagram right there, it's creating that photon. That's why that's omega prime. Then we get the final atomic state, which is B. That's contained inside the N here. Then we get the momentum dotted into the epsilon hat prime complex conjugated, because the complex conjugated part is what contains the creation operator for that outgoing photon. The phase factor, it's going to be e to the minus I k prime dot x, but again, it's dipole approximation, so eliminate that. And then here's the intermediate atomic state appearing there. So this gives us then the product of these 2 then takes care of the numerator of this expression in the case of the first diagram, case 1. And so to complete the story for case 1, we just need the denominator, the energy difference for the denominator. So it's EI minus EK, and that's easy to work out. EI is the energy of the initial state. Again, from the Feynman diagram, that's easy. It's the energy of the atomic state A plus h bar omega for the incident photon lambda. And we subtract the energy of the intermediate state, which is just EI. That's all it is. And we can write this as h bar times omega minus omega IA, where omega IA is the Einstein frequency connecting the atomic states A, initial atomic state A, and the intermediate atomic state I. Now, this was summed over all K, but for case 1, the sum over K just turns into a sum over the intermediate atomic state I, because that's all there is left inside that K. The rest of it's just vacuum. So if we put this together, then what we get is for the case 1 contribution, we're going to get, as you can see, we can get squares of these prefactors. We get 1 over root omega prime, and then a product of these matrix elements. And I'm going to write it this way, and then divided by this denominator. And so it turns into this. It turns into E squared over m squared c squared times 2 pi h bar c squared over volume V times 1 over the square root of omega prime times the sum on intermediate atomic states only now. That's what's left over the sum. We then have, I'll write it this way, as epsilon hat prime star dotted into B sub pi times epsilon hat dotted into P sub IA divided by h bar times omega minus omega IA. And here I'm using a notation, for example, atomic state B, epsilon hat prime star dotted into momentum P, A, like this. The polarization vector here is a C number, which we can take out of the matrix element. And I just write this as epsilon hat prime star dotted into P sub BI, where the P sub BI just means the matrix elements of the momentum between the atomic states, P and I. It saves some writing to do this. In any case, if I do this, then I get this expression for the case 1 contribution. to the matrix element, which is to be added to what we had earlier for the K2. So we're taking care of K2 here, that term, and we've taken care of one of the two cases of the sum. Okay. And now, in case 2, I'll omit the details. You can I encourage you to go through it yourself, make sure you understand it. In case 2, though, the analysis is extremely similar. We get, again, the e squared over m squared c squared. The prefactors are the same. 2 pi h bar c squared divided by volume v. We get 1 over root omega omega prime. And now we get a sum over intermediate states. And what we end up with here is an epsilon hat, not a prime star one, epsilon hat dotted into pbi. And then an epsilon hat prime star dotted into PIA, excuse me. And then this is divided by, and it has an overall minus sign. I'll put that there to emphasize it as an overall minus sign. And it's divided by h bar times omega plus omega IA. It's omega prime plus omega IA. Okay, and that's case 2. Now somewhere here I have a summary sheet of all of this, gathering all the work together. And let me make sure I'm not getting too much extra junk here to get in the way. So here's the summary sheet of the 3 Feynman diagrams and their corresponding amplitudes. These are all amplitudes that add up to the total amplitude. It looks like it's maybe not focusing too well. Let me try focusing it again. Okay, good. All right. So here's the diagrams. This is the seagull graph. These are the other 2 graphs. And there's a common prefactor. There was an m squared. Well, in the first one, in the first factor, I just had an m here, not an m squared. In these other factors, that extra factor of m is appearing there, and the h bar got pulled out of the denominator as an h bar omega. Anyway, that's where the 1 over m h bar came from. Anyway, then these then are the 2 contributions. Otherwise, this is just a summary, copying down of the formulas that I worked out this one in detail, and I just quoted this one. All right, so that's the calculation then of the matrix elements which contribute to the transition amplitude. All right, and their associated Feynman diagrams. If you get used to this, you can write these amplitudes down just by looking at the Feynman diagrams. A little bit of familiarity with the process. Now then, let's go back then, and let's see here what I have here. Let me. Again, I'm messing myself up here because I had too much stuff here. Put that over there. So if we do all of that, then we can come to a summary of a way of summarizing what we've done so far. And it's below this line on this page. The effective transition amplitude is this same time-dependent factor we've talked about quite a bit. We square that, we're going to get conservation of energy. We get these common prefactors, which I split off earlier from all 3 of these contributions to the amplitude. One of the reasons for, and then what's left over I just call M. M just stands for matrix elements, because that's what it's full of, is matrix elements. But the factors that I split off, I designed it in such a way as to make M dimensionless. This is just my notation for it, and I don't know if any books use that, but it's convenient to have this be dimensionless, so I did it that way. And then here is the explicit expression for M, and it's just an accumulation of the formulas we just finished working out. And here are the corresponding Feynman diagrams below the 3 major terms. Okay. Seagull diagram notably is a Kronecker delta in the atomic states. So if you have inelastic scattering where B is not equal to A, then the seagull diagram doesn't contribute. It only contributes to elastic scattering. All right. Now the next task then is to square this this transition amplitude to get a transition probability, and then to sum it up in order to get observable quantities. We're going to be interested here in the differential cross section, of course, because this is a scattering problem. And so now the next step is to actually calculate that. So allow me to do that now. So the first thing to do is to square this Cn. Let me do it this way. If I can, I'll tell you what, I'm going to do it this way. I'm going to save this. Here, I need a place to store paper. Here, like this. Let's do it this way. Let's take this expression for Cn, and let me just square it to get a probability. So the probability n as a function of time is just Cn squared. So I square this time-dependent prefactor. That's the same thing we've done before. It's 2 pi t over h bar squared times this pseudo delta function, capital delta t of omega ni. But that was omega minus omega prime minus omega ba. That's what it was. Difference between the initial and final energies. And then what's left over then is the square of everything else. So let's get that down. We've got, let's see, allow me to make a digression here. I'm going to come back to this and make a digression here. The reason is that this quantity E squared over MC squared has a physical interpretation, and it appears quite a lot. So let me make a digression on that. E squared over MC squared, as it turns out, has dimensions of distance, and it's called the classical radius of the electron, and I'll denote it by Re. And I want to use a better pen for this. Classical radius of the electron. And it's called classical because the expression for it doesn't involve any factor of Planck's constant. It has an interpretation which I'll explain to you. I think I've mentioned this before, but the electric field from a point particle of Hebbe's Coulomb's law gives rise to an energy density E squared. E squared over 8 pi is the energy density, such that if you integrate it over all of space, you get an infinite answer. So if you believe that energy is equal to mass in accordance with relativity theory, then the amount of energy contained in the field of a point particle is actually infinite. And this is a severe interpretational difficulty in classical electrodynamics. In fact, it's usually it's understood that this is a difficulty that cannot be resolved in classical electrodynamics. It requires quantum mechanics and renormalization theory to make sense of this. But in any case, it troubled people even before the advent of quantum mechanics. And an obvious solution is to make a cutoff in the radius. The infinity comes from the very strong electric fields near the particle itself. So an obvious solution to this would be to say, well, maybe Coulomb's law is not valid at short distances. Maybe the singularity softens out at a certain radius, and that inside there's a different formula. And for example, it might just become a constant inside the electric field. And if that were so, then you could end up getting a finite answer. In fact, it even raises the possibility that the observable mass of the electron is nothing but the mass energy contained in the field. A rather appealing idea, which unfortunately is not the true situation is nowhere near as simple as that. But that's an idea that was pursued at a certain point in history. In any case, if you work out what that radius has to be, where the Coulomb field must get cut off or truncated, the divergence must get cut off in order to make the mass equals energy of the field equal to the observable mass of the electron, then you find that radius is this. That's what this is, this classical radius of the electron. It's roughly something like about 2.8 times 10 to the minus 13 centimeters, which coincidentally is about the size of a nucleus. I don't think anybody thinks there's anything to that more than just a coincidence, but that's what it is. It's of that size. So this is one of the characteristic lengths that occurs in problems of this sort. There's a classical radius of the electron, and it's making its appearance here in this transition amplitude you see. While I'm on the subject of these length scales, let me mention a few more. There's also the Compton wavelength, lambda c, which is h bar over mc, like this. I explained the Compton wavelength to you last semester to remind you, if you have an electron and you confine it, or a particle, and you confine it to a box of size L, then of course it acquires a momentum which is of the order of h bar divided by L, by the uncertainty principle. If you make the size L smaller by squishing the walls of the box in, you can force the momentum up, and you can make it as high as you want. You can even make it relativistic. In fact, when P becomes of order mc, you've achieved relativistic momenta just by the uncertainty principle. Well, solving for L, that gives you L is equal to h bar over mc, which is otherwise the Compton wavelength. So the Compton wavelength is a scale length upon which, now we're speaking of electrons here, although the same logic applies for any particle, but for electrons, the Compton wavelength is the distance scale at which the quantum dynamics of the electron is becoming relativistic. And this is something like 10 to the minus 11 centimeters. And then finally, there's the Bohr radius h naught, which is equal to h bar squared over me squared. And you know what that is? That's roughly about 10 to the minus 8 centimeters. It's about half an angstrom, 10 to the minus 8 centimeters, very roughly. So there's these three length scales, and it turns out they're related by factors of alpha, the fine structure constant. Both of them are. If you take the Bohr radius a naught and you multiply by the fine structure constant, you get the Compton wavelength lambda c. If you take lambda c and multiply it by the Bohr radius, you get the classical radius of the electron. So the classical radius of the electron is equal to alpha squared times the Bohr radius, which is roughly about 10 to the minus 4 times the Bohr radius. You see, it's quite a bit smaller. It's done by a factor of alpha squared. So this is just some digression then on length scales. Obviously, given any length scale, you can multiply by any power of alpha, and you get a whole hierarchy of different lengths. But these are three of them that are important in this discussion that we're dealing with tonight. So to go back to where we were doing something rather simple. We were just squaring this transition amplitude to get a probability, and I came to this factor here. But this factor here is the classical radius of the electron. So now allow me just to write RE squared there to save writing. This factor here, 2 pi h bar c squared over volume v, we'll square that. We square the 1 over square root, we get 1 over mega prime. And then what's left over is the absolute value of the matrix element squared. And I won't bother to write that out because it's rather long. But anyway, abbreviating m, we get this result here, like so. There's my digression. Now then, what we're really interested in, as I mentioned, is a differential cross section. Let's draw a picture here. Axes x, y, and z. Let's suppose our atom is here at the origin of the coordinates as initially in state A, and there's the photon that comes in and has a wave vector k and has a polarization too. It interacts with the atom. The atom may transmogrify into a state B, and then there's an outgoing photon going out like this. Let's choose an outgoing direction. Let me call it n hat final. And let me put a small cone around that outgoing direction. And let's call the solid angle delta omega prime. I put a prime on this delta omega because the primes here are referring to the outgoing photon, its mode and its wave vector and everything. So that's why there's an omega prime here. In any case, to obtain a differential cross section, we basically want to sum the probabilities Pn, where n, the final state, includes all final states whose k vector lies in this cone. The n, by the way, I'll remind you, is the same thing as b lambda prime. So it's the k prime contained in the mode lambda prime should lie inside this cone. That's the sum we want to make in order to get the transition rates we need to get a cross section. Well, now I've kind of got this digression that's in the way, but to save paper, let me try to put this all on the same page here. and I'll continue the calculation down below. Here's what we need to do. We want to compute. Let me refocus this. It also has the effect of making it brighter. We want to compute d sigma d omega prime, the cross section for the scattering of the photon in which the scattered photon goes out into a direction indicated with a prime. That's what the omega prime means here. And of course, this depends on polarizations as well. It also depends on the states A and B of the atom that are involved. This can be written as 1 divided by the incident flux times the differential transition rate dw d omega prime. Let's make a little digression. We have space up here to do it on the incident flux. The incident flux is the number of incident particles per unit volume, which I'll call n incident, times the incident velocity, which I'll call v incident. In this particular application, we have 1 photon in our box. We're using box normalization. So the n incident is 1 over volume v. And the speed is, of course, the speed of light because they're photons. So J incident is equal to c divided by the volume v. And so therefore, this thing becomes equal to the volume v divided by the speed of light times dw d omega prime. Well, that's 1 divided by the solid angle of the cone, delta omega prime, and divided by time. We need to divide by time because w is the transition rate. And what we've got so far up here are probabilities. We want to sum the probabilities and then divide by the time to get a rate. So that's why we're dividing by time here. What we want to sum over is all k prime vectors contained in the cone. And then what we sum is this Pn of t, which I'll write out explicitly here. 2 pi t, I'll just copy it, 2 pi t over h bar. It's kind of a long list of stuff here. We've got delta sub t of omega minus omega prime minus omega BA. We've got classical radius electrons squared. We've got 2 pi squared h bar squared c to the 4th divided by the volume squared, squaring this factor up here. We've got 1 over omega omega prime, and then we've got the square of the matrix element m prime. So this is the calculation. Now, as usual in this business, we're going to take this sum over the cone, and we'll let the volume go to infinity. And if we do, this turns into the density of states, which is v over 2 pi cubed, times the 3-dimensional integral of k prime over the cone. But the angular integral just gives me delta omega prime because the cone is small. And what's left is a radial integral in the magnitude k prime of the k vector of the outgoing photon. But if I divide by c cubed, that converts it into a frequency integral. So this is integral 0 to infinity of omega prime squared d omega prime. This is what's left over, the Jacobian in k prime space after we've done these conversions. Then, as usual, we will take this delta function, allow t to become long enough to turn it into a genuine Dirac delta function. This should have been omega prime minus omega here. Omega prime minus omega BA. Let me make sure I'm doing this right. I didn't do this right. Here, let's get it right here. It's the final energy minus the initial energy. So it's omega prime plus omega BA minus the initial energy omega. That's how it works out. So that's what this should be as an argument of these delta functions. Now then, the rest of this is just doing the algebra to pull this together. It isn't so bad. It actually simplifies a lot. Here's how. Reading from left to right, we start with the volume factor there in the numerator. There's another one here from the density of states, which nicely cancels with the v squared in the denominator. And of course, all the volume factors had better go away, and they, if we're doing it right, and they do, because the boxes don't matter. We got a delta omega prime that in the denominator that cancels with 1 in the numerator. That had to go away. We've got a time here in the denominator that'll cancel with a time which is right there in the numerator, giving us a transition rate. Actually, not a rate, and not until we can replace the capital delta function by a Dirac delta function. And as I explained earlier, that has to do with waiting long enough to get rid of transients. I'll gloss over that now, but that's what happens. When that happens, then we really have a transition rate. Other simplifications occur. We've got a 2 pi there, a 2 pi squared there, and a 2 pi cubed in the denominator, and so they all go away. We've got a speed of light c there. A c cubed makes a c to the fourth, but that neatly cancels with that c to the fourth. We've got an h bar squared there in the numerator, and we should have one in the denominator somewhere else. Where was that? It is right. That should have been a squared. That goes away. Okay. And the Dirac delta function, of course, is going to mean that omega prime will get replaced by omega minus omega BA. So omega prime takes on a definite value after we do the integral. So the integral is going to cancel the delta function. And anyway, and you see there's omega prime squared there and 1 over omega prime. Combine those two together, you get omega prime over omega. Anyway, just do all that. And we end up with something that looks not so bad, which is this. It's d sigma d omega prime. It's the classical radius of the electron squared times omega prime over omega times the square of the matrix element m, which of course is complicated, but we wrote it down earlier. And so we've got it on file now what that is. Anyway, this is the result. Perhaps I should bring back the formula for m just so you can contemplate it again ever so briefly. Here it is. Let me separate it off. This is the formula for the dimensionless set of matrix element stuff, m here, this whole thing here corresponding to the 3 Feynman diagrams. And that's what gets squared. Of course, in squaring it, you add the amplitudes first and then you square. Those are the usual rules for quantum mechanics. So there's going to be cross terms and so on in computing the overall cross section, the interference terms between the different contributions to the amplitude m. All right. This resulting formula is called the Kramers-Heisenberg formula. Kramers, S on Heisenberg. It has some interesting history. This formula was actually worked out before modern quantum mechanics in 1925 by who else but Kramers and Heisenberg. They used what was called the old quantum theory, rather inadequate ad hoc collection of rules that got some things right about quantum mechanics, and they used it to do this calculation. Rather remarkable they could even do that. And part of the significance, some of the major significance of this is that in the process of going through this calculation, Heisenberg came to the realization that the fundamental difference between quantum mechanics and classical mechanics is that in classical mechanics, observables commute, whereas in quantum mechanics, they don't. He could see that they were represented by matrices, the observables in quantum mechanics, and just by the machinery of this calculation. And so he conceived of a new version of mechanics, which he called matrix mechanics, in which classical observables were replaced by matrices. Now, of course, nowadays we think of them as operators, and the matrices are the matrices that you get by expressing those operators in some basis. But anyway, he thought of them as matrices, and that was therefore the name of this new idea. Heisenberg was fully aware of the revolutionary nature of of his discovery. It was very clear to him that this just transformed everything in physics. Heisenberg, in collaboration with Pauli and others, used this new matrix mechanics almost immediately to solve various problems like the hydrogen atom, which is an extremely non-trivial problem to do by matrix mechanics. Pauli was the one that did it. He solved the hydrogen atom using matrix mechanics and got the entire Balmer-Bohr results as well as everything else by genuine true quantum mechanics. So in any case, this is important historically for that reason. Let's see. So among the comments to make about this is that the look at the length scale. A cross section, of course, has to have dimensions of area, and we see that here from the classical radius of the electron, RE squared appears here. M was dimensionless, and omega prime over omega is dimensionless too. If the quantum numbers of the initial and final atomic states aren't too different, then omega and omega prime are both of, we're speaking of optical photons, so they're both optical photons. This ratio is of order unity. And so if the quantity M, dimensionless quantity M, is also of order unity, then this cross section for photon scattering is of the order of the square of the classical radius of the electron. However, I just explained that RE goes like alpha squared times the Bohr radius. So RE squared is equal to alpha to the fourth times the square of the Bohr radius, which is something like about 10 to the minus 8 or 10 to the minus 9, maybe, the Bohr radius squared. Now, the square of the Bohr radius is basically the cross-sectional area of an atom. So when the photon comes in and sees the atom, the effective area that it sees is down by a factor of 10 to the 8th or 10 to the 9th, compared to what you might call the geometrical cross-section of the atom. It's really small in comparison to the size of the atom. In contrast, if you want to talk about two atoms scattering, such as an HH atom scattering on each other going to HH, or let's say electrons scattering off a hydrogen atom, if the energies were not too large, the cross sections for these types of processes would be of the order of the Bohr radius squared. It's kind of like what you'd expect about the size of the atom. But the photon scattering cross section is much less. So this is the explanation for why ordinary gases, such as the nitrogen and oxygen in the Earth's atmosphere, those of course are molecules. The explanation for why the gases in the Earth's atmosphere are transparent, mostly transparent to optical radiation. They allow the sunlight to penetrate straight down to the surface of the Earth without much getting in the way. Thinking about processes like two atoms colliding, we'll think about two molecules colliding at ordinary pressures at the surface of the Earth. One air molecule doesn't travel very far before it bumps into another air molecule. It's a small fraction of a millimeter is the mean free path. But the mean free path for a photon is going to be, based on this scaling, something like 10 to the 8th or 10 to the 9th times as large. And so this turns into something like, I don't know, 30, 40, 50, 100 kilometers, 50 kilometers anyway, something like that. That's the decay length or the mean free path of a photon traveling through air at STP, which is why you can see mountains in the distance, 20 miles distant away and things like that. Now, of course, when the sun is setting, the sunlight is passing through thick layers of atmosphere, and there is a significant fraction of the light that is, which is it's actually scattered by the sunlight. I'll come back to that later on. But if you make a thick enough layer of air, you do absorb photons. But in any case, it's this small factor that's the explanation for that great difference in the mean free paths. All right. Now, here's another, speaking of orders of magnitude, there's something else to be said. This estimate that I just made of the order of magnitude of the cross section as being in atomic units, you see it's alpha to the fourth, because A naught squared in atomic units is just 1. In atomic units, it's alpha to the fourth. This estimate that I just made assumes that the quantity M is also of order unity. Well, let's go back and look at the quantity M. Here it is. The basic ingredients that go into this are all just things they're just atomic stuff. There's nothing that goes outside the atom. These are atomic states A and B here, intermediate state I, and polarization vectors of order unity. Momentum operator is of order unity if the atomic quantum numbers are not too far away from the ground state. So most of everything you see here is of order unity in atomic units. On the other hand, there's these denominators, especially the denominator on this first Feynman diagram is interesting to look at. This is omega minus omega IA. The I is an intermediate state. The A is the initial state, as you can see from the Feynman diagram. You might think, for example, let's suppose the initial state A were the ground state of the atom. It might well be. The I here is an intermediate state, and you sum over all of them. This includes the ground state, but the rest of them are all excited states. So this omega IA, then, if I is an excited state, this is the Einstein frequency connecting the ground state to one of the excited states. Omega here, on the other hand, is the frequency of the incident photon, which you could vary and make anything you want. So if you made omega equal to or close to an omega IA, what it means is the energy, or the energy of your incident photon is getting close to the energy needed to lift the atom from its ground state into one of its excited states. That's where this denominator gets to be small. And under those circumstances, this first term is going to get large. And in fact, it'll dominate over the other two terms. And it'll call into question this ordering scheme, particularly this alpha to the fourth that I just spoke of. In fact, you can see that as omega approaches omega IA, this term is going to dominate and get bigger and bigger. So if we made a plot of the cross section as a function of the incident photon frequency omega, d sigma d omega here, like this, and we've got one of these resonant frequencies omega IA, there's kind of out here, I call this the desert out here, where you're not near any resonance at all. In atomic units, you're of order alpha to the fourth power. Very low cross section out here in the desert. But as you come closer to the resonance, the cross section increases, and in fact, our formula nominally predicts that it goes to infinity, like so. So near resonance, the ordering or estimate of the size of the cross section changes, and we have to worry about that. I'll come back to that at a later point because I want to cover some other things first. But anyway, that's an issue that needs to be resolved, that we need to study in connection with order of magnitudes here. Let me just point out a few other things here. Squaring the matrix element M in the neighborhood of resonance is going to give us the square of that denominator. And therefore, the nominal prediction of the Kramers-Heisenberg formula is that if the incident photon frequency is exactly on resonance, that the cross-section then goes to infinity. Well, that's non-physical, and we can't believe that's really true. So on this dotted line, the nominal prediction is that it goes to infinity, but some physics has to round it off somehow. And so one of the questions we have is how high does it actually go? Another question you have is that as we come closer and closer to this resonance, at some point, the Kramers-Heisenberg formula has to break down because it can't be true exactly at resonance. So there's some presumably small distance here within which the formula breaks down and is no longer correct. And so another question is how close do we have to come for that to be true? And then finally, there's a third question which is what's wrong with our derivation that we get these non-physical divergences? In my last lecture, somebody asked me about those denominators in the perturbation theory, and he said, what happens when they go to zero? Well, that's exactly what is happening here, is where these denominators are going to zero. So it's directly related to that earlier question. All right, I'll return to this later, but for now, what I want to do is to say some things about the Kramers-Heisenberg formula in more general terms. Let's see. Let's go back to. Let me see here. Trying to keep track of all my stuff here. Let's specialize to the case of elastic scattering. I'm going to go over this as briefly as possible and just summarize the results. The algebra that's involved here is somewhat lengthy and would definitely take me quite a bit of a lecture to cover it in detail. And I think it's actually ultimately not that interesting. It's all given in the notes in case you want to see it in detail, but I'll just summarize the results. Let's take as a special case elastic scattering in which the final state's the initial state. Initial state A may or may not be the ground state. It doesn't have to be the ground state. then the Kramers-Heisenberg formula simplifies a little bit because the omega prime over omega becomes 1, and this is what we get for the cross section. The matrix element M simplifies a little bit too, and in fact, you can take. It turns out that you can take the seagull diagram, the first term, um, the seagull diagram. Go back. It turns out that in the case of elastic scattering, the delta AB is 1. You can take the dot product of the polarization vectors and you can convert it into sums. You can combine it with these two sums like this. If you do that, and if you use this trick to convert momentum matrix elements into position matrix elements by using this commutator, this is a trick that we dealt with in when studying spontaneous emission in an earlier lecture, then go through the algebra. It turns out that this ends up being the expression for the quantity m, that same quantity m we had earlier. This is it. It's the same m that goes into the Kramers-Heisenberg formula. Now only has 2 terms instead of 3. Also, the sum is now restricted only to states that are different from A, because the state that's equal to A actually vanishes. So you might as well restrict it that way. Well, in any case, there's no approximation in this. This is just taking the elastic scattering where B is equal to A. But having gotten that, we can now make some interesting approximations. One of the approximations that's interesting to make is to assume that the frequency, take the low frequency limit of low frequency photons incident upon our atom. Let's suppose, to be specific, that the state A actually is the ground state. Let me draw it down here like this. Here's A, and then here's an excited state I, and then here's another one I prime, and so on. There's an infinite number of them, but there's a first one. Let's call this first one here the first excited state. Well, let's suppose that our h bar omega gives us just a small fraction from the ground state to the first excited state. That would mean that the ratio, that omega was much less than any omega IA, and it would mean that we can neglect the omega IAs in this expression here, and then you can work out what this is. If you do that, you can then you neglect the omega. Did I say you wouldn't neglect? Excuse me. If omega is much less than any omega IA, you neglect the omegas in here. It turns out that if you do that, then the leading term here, the constant term here, actually vanishes, and you need to go to next order in this ratio of omega over omega IA to get a non-zero result. And if you do that, then gives you a factor of omega squared, because it combines up here with that. And so going through the algebra of that, then what you find a leading order in this limit of small frequencies omega is a new m. This is now an approximation to what's up above. Is it looks like this. And it's got an omega squared in it, and everything else here is independent of omega. So the main point to make here is that this m is now proportional to omega squared, but the cross section goes like m squared, so that means the cross section d sigma d omega prime is proportional to omega to the 4th power. Well, this 4th power dependence at low, so this is the characteristic frequency dependence of scattering or radiation at low frequencies. And this is called Rayleigh scattering. Rayleigh scattering has this characteristic frequency dependence. Rayleigh derived his scattering not by quantum mechanics. He was a classical physicist. He lived in the decades before quantum mechanics arose. But he studied scattering of electromagnetic waves by small particles, and he obtained this omega to the 4th dependence. So we call it Rayleigh scattering. Rayleigh scattering actually applies to sunlight passing through the Earth's atmosphere. The idea is that the A here, this ground state A, is the ground state of the N2 or O2 molecules that exist in the Earth's atmosphere, whereas the first excited state, the first electronic excited state anyway, is in the ultraviolet. So the visible light, which is coming from the sun, has got an h bar omega, which is only some fraction of the distance to the first excited state. It's not exactly very much less than this distance, but it's maybe a half or a third or something of it. So crudely speaking, at least, this formula then applies in that case. And in that sense, optical frequencies are quote unquote low frequencies, and Rayleigh scattering applies. However, because of the omega to the 4th dependence in the cross section, it means that the high frequency optical radiation, i.e. the blue light, is more strongly scattered than the red light is. If you figure the ratio of frequencies between red and blue is about 2, the cross section is about a factor of 16. You see, blue light's much more likely to be scattered. So that's why the sky is blue. It's because when you look at in the sky in direction, not in the direction of the sun, what you're actually seeing is sunlight that's scattered by air molecules in such a way that the scattered photon goes into your eye, and it's predominantly blue light, which is scattered. Conversely, when the sun is setting so that it's on the horizon and you look directly at the sun, you don't want to do that when it's overhead, but if it's on the horizon, it's okay, because the sunlight's passing through thick layers of air. And as it does so, the blue light is mostly scattered out, is eliminated from the beam coming to your eye. And so what's left over is the red light, which is why the sunsets are red. So it's this omega to the fourth dependence or Rayleigh scattering, which explains not only why the sky is blue, but also why sunsets are red. All physics students have to learn this at some point in their career. Because you never know, your grandchildren are going to ask you, hey, Dad, you know, you're a physicist, you should know this. Why is the sky blue? Okay, now one time I visited a solar energy installation. It was actually in Israel. It's one of these where they have an array of mirrors, a field of mirrors that focus sunlight on a tower, atop of it has to be at some altitude, top of a tower. And a great deal of high temperature, a lot of heat is generated that way. You can get very high temperatures this way. But of course, the mirrors have to have motors on them to track the sun, so they keep focused on the spot. So it's kind of a complicated system. There are solar installations like that in California, actually in Southern California, also in Spain, and maybe some other places too I don't know about. But what's interesting is that as the sunlight focuses, as the light from the mirrors comes to a focus near the top of the towers, you can actually see it. You can see the beam. And the people I spoke to said that they believe the beam it's not caused by scattering from dust. It's caused by Rayleigh scattering. The intense light passing through the air scatters it into your eyes, and you can see it. I asked the guy I was talking to, whether or not birds get caught in it. If they did, it'd be bad for them because they'd get roasted right away. And he said, no, the birds are too smart. They don't go into the beam, but the bugs do. They're too dumb, and they just immediately just puff up into a puff of smoke. They get eliminated that way. Anyway, I can't think of Rayleigh scattering without thinking about that, so I'll leave you with that image. All right. So those are some aspects of Rayleigh scattering. This omega to the fourth dependence, by the way, is kind of what's happening as you approach the resonance, as the differential cross section curve is rising towards the resonance. That's the behavior of it. If you're not too close to the resonance, that's the idea here. Let's see. There's something else we can do with elastic scattering. To do that, it might be best to go back to the original formula for the cross section. Allow me to do that. Here it is, or the original formula for. Here's the original formula for the matrix element given here. I won't rewrite it, but let's take the elastic. Let's specialize it to elastic scattering so that we get the dot product of the polarization vectors here. The delta AB is 1. And over here, we just replace the B's by A's in both places, and omega prime becomes omega. Anyway, if you do that, you get the M for elastic scattering. Now, let's consider a different limit. Let's consider a limit in which omega is much larger than any omega IA. Let me write it over here somewhere. Let's consider the case where omega is much bigger than any omega IA. So let's suppose A is the ground state, and again that the I's are excited states. Maybe there's more than one of them here. This is effectively saying that H bar omega is much bigger than the binding energy of the electron, which if we're doing hydrogen, as you know, would be 13.6 electron volts. Let's suppose we have a reasonably high energy photon like that. Then what that would mean is that these two complicated terms with the sums and the complicated Feynman diagrams would, relatively speaking, become less important than the Seagull graph because of the omega in the denominator. So omega gets bigger, these become negligible. So in that limit, we're simply left with the Seagull graph, which in elastic scattering has just got the epsilon epsilon prime. And so in that case, what we get is d sigma d omega prime is the classical radius of the electron squared times a very simple result, just the dot product of the polarization vectors squared like that. And the physics of this is that if the photon energy is much bigger than the binding energy of the atom, then it's almost as if the electron is might as well be unbound. It doesn't even care that it's bound to the atom. And so we end up, by this means, we end up obtaining the cross section for the scattering of photons off of free electrons. This is otherwise called Thomson scattering. This is the Thomson cross section. And this is the formula for it. It's as I say, it just comes from the Seagull diagram alone. Thomson scattering is quite important in a number of applications. For example, photon transport, energy transport by means of photons in the interior of stars. The photons are mainly scattered by free electrons, and the Thomson cross-section governs that process. You know, they do a diffusion, scattering, multiple scatterings, diffusing as they migrate out towards the surface of the star. That's just one example of an application of Thomson scattering. The derivation of Thomson scattering we've been using has used non-relativistic quantum mechanics. That means that the energy of the photon has to be much less than mc squared, where m is the mass of the electron, because otherwise our formalism isn't valid. On the other hand, there is a relativistic generalization of Thomson scattering. It's called Compton scattering. It's the same process, except if you use the word Compton, it implies that this condition is no longer true, but rather it's greater than or comparable to mc squared. And there's moreover a generalization of the Thomson cross-section to the relativistic case. For this, you need to use the theory of the Dirac equation instead of the Schrödinger equation. And the corresponding formula is called the Klein-Nishina formula. It's one of the early results in the theory of relativistic quantum mechanics, was the calculation of this cross-section. All right, anyway, that's some aspects about Thomson scattering. I'm almost out of time. I've got maybe one more thing I want to say. I thought there was something else I wanted to say about Thomson scattering. I can't remember now. Let's see here. Let me get these out. Let me say something else about, I'll give you an example of inelastic scattering now, and I'll outline this in the most schematic terms possible because I don't want to go into detail. I'd like to talk about Raman scattering, which is an example of inelastic scattering. Here's a typical experimental setup. You have a tube of molecular gas, and you have a laser light which passes through it. It has some frequency omega-0 beam of laser light. And you take some point along the beam like this, and you go off at some angle theta that you're interested in, and you have a detector in which you look at the scattered radiation. So the photons are coming in like this, and some of them are scattered in the direction of your detector. This is the basic idea. If we make a plot as a function of omega prime, let's see here. Let me call this omega because I'll just call it omega without the naught on it. This is the frequency of the incident photon, and omega prime is the incident frequency of the scattered photon. And we plot d sigma d omega prime as a function of the energy of the scattered photon. That's the energy of the photons detected by our detector. Then at omega, which is the incident frequency, you get a strong spike there. This is, of course, corresponds to elastic scattering coming in. However, you typically also find sidebands like this at a frequency omega plus delta omega, and another one at omega minus delta omega. And in case you hear anything, that's my cat yowling. So I have to feed her as soon as I'm done here. Anyway, so what are these sidebands? Well, let's suppose the gas is a diatomic molecule, in which case it's got vibrational degrees of freedom with a vibrational frequency omega vibe, and the motion is roughly that of a harmonic oscillator. What's happening here is, as I said, most of the scattered photons are elastic. However, however, the gas that's in here has a distribution of vibrational energy states, which is based on the temperature of the gas and the Boltzmann factor and so on. So there's different vibrational quantum numbers of the molecule, and it's possible for the molecule to undergo an inelastic collision in which let's say it absorbs energy from the incident photon. If it does, it raises it to the next vibrational state, and so it absorbs energy h bar omega v, and therefore the scattered photon has an energy which is less than that. And I think I've got this backwards now. This should be higher and this should be lower. This sideband is higher and this is lower. Yes, this sideband is called these are called Stokes lines. Here, there's a central one. The Stokes lines is the line which is lower than the central frequency, the elastic scattering frequency, and the other one above it is called an anti-Stokes line. That's the terminology people use for this. But the physical explanation for the Stokes line is that the molecule absorbed one quantum of vibrational energy, and so the scattered photon lost that amount of energy, and that's why it's at a lower frequency. On the other hand, it's also possible that the molecule might have given up a quantum of vibrational energy, dropped into a lower vibrational state, and therefore added to the energy of the scattered photon, and that's what you get here with the anti-Stokes line. Now, anyway, so that's the story of Raman scattering. It's a version of inelastic scattering. I think my original position in these lines is I'm not sure I'm doing this Stokes lines, anti-Stokes line business correctly. I'll correct that in the next lecture, which there'll be opportunity for, because we're just about out of time tonight. Anyway, that concludes almost everything that I wanted to say about the Kramers-Heisenberg formula. Oh, no, it doesn't either. There's still quite a bit I want to say about the resonance phenomena, what happens when you're close to resonance. And so I'll address that issue in the next lecture. And when that's done, we'll turn our attention to relativistic quantum mechanics. So are there any questions about what we covered tonight?
Professor,
Yes.
is there any intuitive reasoning to say why the Stokes line has different height compared to?
Yeah, that's what I want to get straight. The reason is this, is that if you want to increase the energy, then you go from some vibrational state to the next one up. And you can do that with the ground state, you see, because if the atoms, if the molecule's in the ground state, if the temperature is low enough, then most of the molecules are in the vibrational ground state. In fact, that's true for nitrogen and oxygen at ordinary temperatures. So therefore, you get a lot of transitions to the next state, which is n equals 1. On the other hand, at ordinary temperatures, there's a few molecules, not very many, that have n equals 1, n equals 2, and so on. Those are capable of making transitions into a lower energy state. So what that means is that the line below, which is the one where we absorb energy from the incident field, is the strong line. That's the Stokes line. The line above, where we release energy, that requires, because of the Boltzmann factor, there aren't as many molecules in that higher state. That's the reason for it. That's what I wanted to get straight. I was afraid I was getting it wrong, but anyway, this I think I said it right now. All right, good. Any other questions?
I was wondering, like, what timescales all of this has been valid for, because I know that the equations we were using for the time dependence are only valid between like less than 1 over a and but long enough that it goes to a delta function. So it's just one, but then at the end all the time dependence cancels out anyways. So I'm not really sure what the story is there.
Yeah. So when we did scattering, we needed to make the time long enough to get the delta function to conserve energy. And the same thing is true here. I didn't go into detail what that means, but that needs to be done. That's because of the artificial transients in our initial conditions. It's really not part of the physics. When we did the spontaneous emission, there was an upper time as well. And the upper time had to do with the depletion of the initial state. When the probability of the initial state got depleted, then this linear prediction for that probability, it has to be corrected. In fact, we expect an exponential curve, although we certainly did not prove that. But this problem is back to scattering again. So the time condition is we just need to be long enough to eliminate the transients.
Okay, thank you.
Yeah, okay. These scattering situations are an idealization. They represent an idealization in which we have a steady beam coming in from infinity that's always been there. Now, you can't do that with a single photon or a single particle. So it's a limiting case. In fact, getting all the limits right is rather tricky, but it's a limiting case where the volume of space occupied by the photon wave function increases, but we wait longer and longer for the whole process to take place. I mean, we talk about a plane wave, you don't really have plane waves. Likewise, well, here I did it with box normalization. If you did it without that, you're reduced to trying to talk about a single photon in an infinite volume of space, and that doesn't actually make any sense. It doesn't make any sense for a scattering of material particle if you want to talk about a plane wave either, because it's not normalizable. It's not a physical state. In my notes on, which I've revised, by the way, I did some revision on that. In the notes on the introduction to time-independent scattering theory, I discussed the idealizations that are needed to bring about these initial conditions for scattering problems. I discussed them at some length. Are there any other questions? All right, so I'll see you next Tuesday, and we will talk about resonance scattering at that point.